This is the 8th video in this series dedicated to Bessey shuffle diagrams. Recall, a shuffle S is said to be a Bessey shuffle if and only if S preserves or inverts Bessey sequences. Recall, the Bessey sequences of order 8 are 1 0 0 1 0 1 1 0 and its inversion 0 1 1 0 1 0 0 1. Also, remember that we have color-coded the 8 position values as follows. Position values 1, 4, 6 are color-coded black, and position values 2, 3, 5, 8 are color-coded red. The reason we do that is because of the structure of Bessey sequences, and that will become clear as we move forward, if that is a new concept to you. Also, we have this set of symbols here representing the situation where cards in positions 1, 4, 6, 7 remain somewhere in those positions, 1, 4, 6, 7, after a particular shuffle is performed. Similarly, the cards in positions 2, 3, 5, 8 also stay somewhere within those same position values. On the other hand, inversion occurs if the cards originally in positions 1, 4, 6, 7 get moved to position values 2, 3, 5, 8 in some assignment, and vice versa. When that happens, we say inversion has occurred, and we represent that outcome as follows. Finally, for a quick review, recall that Bessey sequences of order 8 have the following structure. So up above I have the 8 position values, and then down below I've indicated where zeros and ones need to be so that the sequence is a Bessey sequence. And there are just 2 possibilities. The ones are in positions 1, 4, 6, 7, and the zeros are in positions 2, 3, 5, 8. Alternatively, if we look at the inversion of this sequence, which is the one below, the role of zeros and ones switch places. The first new shuffle for today is called a judicious push-off of pairs, with stacking as indicated here. So let's go ahead and demonstrate this shuffle while simultaneously deriving its permutation. So we begin with an ordered packet 1 through 8 and perform our shuffle. Okay, so if you watched the previous video in this series, you've already been introduced to push-off pairs as a way to mix a packet of cards. Now the J here is for judicious, which simply refers to the fact that we will be stacking these in a way that's more complicated than just left to right or right to left. Okay? So push off pairs, how does that work? Well, you just push off the top 2 cards without changing their order, maintain their order as is, set those down, and then push off the next 2, set those down, push off the next 2, set those down, and then the last 2 go down last. Now the stacking is a leapfrog stacking that we've seen before. So pile 1, so this is pile 1, 2, 3, 4. Pile 1 leaps over pile 2 and gets stacked on top of pile 3. Pile 2 leaps over this pile and gets stacked on top of pile 4. So that's what we've indicated up here. And finally, in this particular mixing of the cards, we're going to stack the left pile on top of the right. Okay, so what is the new ordering of the packet? And from there, we can actually write a formal description of the permutation. So the new ordering is 1, 2, 5, 6, 3, 4, 7, 8. So using Cauchy's two-line notation, we obtain the following representation. The bottom row here is the new ordering that we've just demonstrated. So 1, 2, 5, 6, 3, 4, 7, 8. Converting this to cycle notation, we obtain the following. 1 goes to 1, so we get a fixed point, or a 1 cycle. 2 goes to 2, so whatever starts in position 2 ends up back in position 2. 3 goes to 5, so we have an arrow from 3 to 5. 5 goes back to 3, so we have this cycling back arrow. So this gives us a 2 cycle, or in other words, a transposition. 4 goes to 6, as we can see right here, and 6 goes to 4. So that completes a 2 cycle as well. 7 goes to 7, so it's a fixed point, or a 1 cycle. And 8 goes to 8, so we have another fixed point, or 1 cycle. Color coding, or cycle notation, of this permutation, we obtain the following. Now remember from our review, digits 1, 4, 6, 7 are color-coded black, and positions 2, 3, 5, 8 are color-coded red. So we get a single cycle, so the black 1 gets sent to itself, which means that the object in that position doesn't go anywhere. Red 2 gets assigned to itself, red 3 goes to 5, and red 5 goes back to red 3. Black 4 goes to black 6, which goes back to black 4. Black 7 goes to itself, it's a fixed point, and red 8 also gets assigned to itself, which is a 4th fixed point. So here we find the following. Each value gets sent to a value of the same color. So what this means then is inversion has not occurred. All of the cards that began in positions 1, 4, 6, 7, in other words, these 2 and the 2 in the middle, get moved back to somewhere among those 4 position values. The same thing with the cards that originally began in positions 2, 3, 5, 8. They return to position values contained in a complement. So in other words, we're looking at this situation here. Since inversion does not occur, we should be able to observe that with our Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0. So what it means is if we perform this shuffle, we will again get that same sequence form 1, 0, 0, 1, 0, 1, 1, 0. So let's go ahead and just demonstrate that. I'm just performing this judicious push-off pairs a second time. Remember, we're doing this leapfrog stacking. So 1 jumps over 2, lands on 3. 2 jumps over the 3rd pile and lands on the 4th. And then we're stacking the left pile on top of the right. So it should be the case that we get 1, 0, 0, 1, 0, 1, 1, 0, which we do. So that sequence form is preserved, even though we do know that the cards, or some of the cards, are moving around among themselves. Okay, so for example, the card in position 1 stays in position 1. The card in position 2 stays in position 2. But the cards in positions 3, which is right there, 3, and 5, which is right here, those 2 cards switch places. But of course, we won't detect anything if both of them are labeled zeros. Similarly, the cards in positions 4 and 6, these 2 right here, technically traded places after this shuffle was completed. And then the cards that were in the last 2 positions, 7 and 8, are fixed points, so they did not go anywhere. Turning to our shuffle diagram, on the left, top row, we find the following. We have these 4 fixed points, 1, 2, 7, 8, and then we have these double arrow lines between 3 and 5, and also between 4 and 6. So that is the Bessey shuffle diagram for this particular shuffle. And we can see that this shuffle has order 2 because it's a product of transpositions. That means if we perform this shuffle twice, we return the packet to its original order.